Hello, cosmic explorers, and welcome back to the channel where we unravel the universe's greatest mysteries. Today, we're journeying to the king of planets, Jupiter, to investigate a theory that's shaking up everything we thought we knew about how giant planets are born. Forget the neat, tidy models you learned in school. We're diving into the shallow core theory, a concept that paints a picture of Jupiter's heart as something far stranger and more chaotic than we ever imagined. For decades, the textbook picture of a gas giant was simple: a small, dense, rocky core surrounded by a massive envelope of hydrogen and helium. Think of it like a cosmic peach, a hard pit at the center, wrapped in layers of gas. This model, known as core accretion, was the leading theory for planet formation. It suggests that a solid core, about 10 times the mass of Earth, formed first, and its immense gravity then pulled in the surrounding gas to create the behemoth we see today. It's a clean, logical process that has dominated planetary science for years. But what if it's wrong? What if the heart of Jupiter isn't a solid pit at all? This is where NASA's Juno mission swoops in to change the game. Since arriving at Jupiter in 2016, Juno has been making incredibly precise measurements of the planet's gravitational field. By flying closer to Jupiter than any spacecraft before it, Juno can feel the subtle tugs and pulls from the planet's interior, and what it's feeling is weird. The data doesn't quite match what we'd expect if Jupiter had a small, well-defined solid core. The gravitational pull is more spread out, more fuzzy. This discrepancy sent scientists scrambling back to their computer models, trying to figure out what kind of interior structure could produce the signals Juno was detecting. The answer they came up with is both elegant and revolutionary. Enter the shallow core, or dilute core theory. This radical idea proposes that Jupiter's core isn't a solid, distinct object. Instead, it's a vast, fuzzy region where heavy elements like rock and ice are mixed and diluted into the metallic hydrogen that surrounds them. Imagine trying to dissolve a spoonful of sugar in a small cup of water. You get a dense sugary solution at the bottom. Now imagine that sugar spread throughout a giant swimming pool. That's the essence of the shallow core theory. The core's material isn't concentrated in a tight ball. It's smeared out over a huge area, potentially extending up to half of Jupiter's radius. This means the transition from the core to the gassy envelope isn't a sharp boundary, but a gradual blended zone. So, how could something like this happen? One of the most dramatic theories involves a colossal impact in Jupiter's distant past. Picture a young, newly formed Jupiter, with its neat, solid core just settling in. Then, out of the darkness of the early solar system, comes a massive protoplanet, perhaps 10 times the mass of Earth, on a collision course. The impact would have been unimaginable, an event of planetary scale violence. This giant impactor would have slammed directly into Jupiter's core, shattering it and splashing its heavy materials up into the overlying hydrogen envelope. The intense heat and pressure from the collision would have vaporized the rocky material, allowing it to mix and blend with the gas, creating the vast dilute core we see evidence for today. It's a beautifully chaotic explanation that turns our neat models of planet formation on their head. This theory doesn't just change our view of Jupiter. It forces us to rethink the entire process of how giant planets form and evolve. If a planet's core can be fundamentally altered by a later impact, it means that planet formation isn't a simple one-way street. It's a dynamic, and sometimes violent process. The shallow core model also helps explain some other oddities about Jupiter, like the strange distribution of certain elements in its atmosphere. If the core's contents were churned up and mixed, it makes sense that we'd find traces of them spread throughout the planet. Furthermore, this has huge implications for understanding exoplanets, the thousands of planets discovered orbiting other stars. We've found many hot Jupiters and other gas giants out there, and we've largely assumed they formed just like our own. But if Jupiter's history includes a cataclysmic, core-shattering impact, who's to say that isn't a common occurrence? Perhaps many gas giants across the galaxy have these fuzzy, dilute cores. It challenges our core accretion models and opens the door for alternative formation scenarios, like gravitational instability, where a clump of gas and dust collapses directly to form a planet without a solid seed. The line between these theories is becoming as fuzzy as Jupiter's core itself. The Juno mission is still collecting data, and with every orbit, it refines our understanding of Jupiter's mysterious interior. We're living in a golden age of planetary science, where a single mission can rewrite the textbooks. The story of Jupiter's core is a perfect example of science in action. We had a theory, we gathered new data that contradicted it, and now we're building new, more sophisticated models to fit the evidence. The universe is always more complex and fascinating than we initially assume. The idea of a shattered diluted core transforms Jupiter from a static, layered ball of gas into a dynamic world with a violent and dramatic history written deep within its heart. It's a powerful reminder that even the largest objects in our solar system still hold profound secrets, waiting for us to uncover them. What do you think about this theory? Does the idea of a giant impact shattering Jupiter's core blow your mind as much as it does mine? Let me know your thoughts in the comments below. We love diving into these cosmic debates with you. Thanks so much for joining us on this deep dive into the heart of Jupiter. If you enjoyed this journey and want to explore more of the universe's incredible mysteries, make sure to hit that like button and subscribe to the channel. Don't forget to ring the notification bell so you won't miss our next adventure. Until next time, stay curious and keep looking up.